At this point, we are ready to define the basic algebraic structures. We have defined what a binary operation is. We talked about its properties, and therefore we can define uh, the, the structure called group. Here we have a set, and it's equipped with one single binary operation. Okay, so the structure is set A along with a binary operation. We call the structure a group if the following three axioms hold. The operation is associative. That's number one. Okay, we know the definition of being associative. Number two, there is an identity element with respect to the operation. Okay, again, we know the definition of identity elements, but now be careful. We are saying an identity. So this means both left and right identity. Okay. And number three, there is an inverse element for every element. Again, I'm not specifying left or right, so this means it should be both left and both right. Okay. This structure we call a group. Now, what you have to be careful here is the operation does not have to be commutative. Okay, you have to be aware of this. It has to be associative, but it doesn't have to be commutative. Let's see some examples. Here's the Boolean group. The elements of the set are 0 and 1, and you can also see these as false and true. And the addition, the operation here is exclusive addition, okay, or exclusive OR. Here, this structure satisfies all the three axioms, so it's a group. Okay, but be careful, this one is not a group. This one is again a group with the operation biconditional, but this one with AND is not a group. You can see by looking at the axioms why these two are not groups. Okay, it's not that difficult. I leave that to you. Another example is a typically set of integers along with the operation addition. Now, this addition here is the usual addition we know of. Okay, it's a group because, well, it's associative, the addition of integers. And we have an identity element, which is 0. And we also have inverse elements for every element. We have, if you have 5, you have -5. If you have -3, you have 3 in the set of integers. On the other hand, set of integers with the usual multiplication is not a group. Why? Because we do not have inverses. Okay, the multiplicative inverse of, let's say, 5 would be 1/5, but it's not an integer. Therefore, we do not have an inverse, which means this is not a group. Of course, if you make it to the set of, let's say, rational numbers or real numbers along with the usual multiplication, that would be a group, except 0. And another typical example is clock arithmetic or modular arithmetic. We have a group when the operation is defined as addition. Okay, what do we mean by clock arithmetic? For instance, let's say you have a clock where you have like 1, 2, 3, 4, 5, 6, or rather you would start counting from 0 in modular arithmetic. Therefore, you should write this as 0, 1, 2, 3, 4, 5. Now, when we say a clock arithmetic or clock addition, for instance, if you would like to add 2 to 1, you just go in this direction by 2. You end up at 3. But if you like to add 2 to 5, then you start from here, go 1, and then go 2. You end up at 1. So 5 plus 2 equals 1 in this group. Okay? And the group of integers modulo n is usually denoted by either this or this symbol. You would actually see this one more frequently. It has to do with the quotient notation because it induces quotient groups, etc. I'm not going to go into those. And by the way, we are going to also come back to this group when we talk about prime numbers, modular arithmetic later on, and we'll see examples or applications regarding cryptography. So this is a very important group with real applications. And another very abstract example to groups is what we call the symmetry groups, or the orientation of a triangle after rotations and flips. This also defines a group, and let's see how we can actually build this. Take a triangle and let's label the corners. Let's say this is 1, and this is 2, this is 3. If I rotate this once in this direction, okay, I get, well, this becomes 3, this 1, and these 2. So I'm going to call this R. Okay, so this is the triangle I obtained after one rotation clockwise. So I'm naming this R. Okay, and I'm going to rename this 1 because it's just itself. Okay, if I rotate it twice, what I get is 2 comes here, 3 comes here, and 1 comes here. So this I'm going to denote as R square. Now, if I rotate it once more, I obtain the original triangle, so that becomes 1. So I do not have a R to the power 3 element. On the other hand, I can also flip this along this axis, okay, flip it around. So if I do it just once, one flip, 1 stays here, and these 2 swap places. Okay, you see this is a new element. This is different from all the others. And of course, if I flip it twice, it becomes again itself. But what I can do is I can apply a rotation to this. Okay, so that will be, if I rotate this once, 1 will come here, 3 here, and 2 here. Now this is a flip applied first and then rotated, RF. If you rotate it once more, that will be 2 here, 1 here, and 3 here. So this is R square F. Now these are the 6 distinct elements you can get. But for instance, if you apply rotation first and then flip, so I'm looking for the element in this way, rotation first and then flip of this original triangle, what you get is actually this one and not this one. So you see the operations here are not commutative. So this is a group, but it is not commutative. If you would like to verify this is a group, what you need to do is you look for all these. Is it associative? Is there an identity? Well, there is an identity. 1 is identity. You do nothing. That's the identity. Is there an inverse? Yes. R is an inverse of R squared and vice versa. If you rotate twice the element R, you obtain the identity. Or you rotate once R squared, you get the identity. Or this one is its own inverse. You apply it twice, you get identity. And you can also find the inverse of these, okay? So it's a group, but it's not commutative. Now, in a group, the identity element, we didn't state it here. We just said there is an identity. We didn't specify a number, but it's unique in a group. Why is that so? Because let's say, assume that you have multiple identities. Let's say E is an identity, and at the same time, F is an identity. So what happens when you multiply them together? I mean, when I say multiply, understand, apply the operation. So this means I'm multiplying E, which is an identity, with F, so I should get F. But at the same time, I'm multiplying E with F, which is an identity, so I should also get E. So you have a contradiction. If you assume E and F are distinct, then This leads to E equals if, which is a contradiction. So you cannot have multiple identity elements. The identity must be unique. Similarly, the inverse of each element is also unique. Why is that so? Let's see. Again, assume X is an element in the set and Y and Z are inverses of this element. In this case, X times Y equals Y times X should be equal to the identity, and X times Z and Z times X should be equal to the identity. Now, let me take this one and multiply it with Z from left. So you get ZXY equals, well, that equals E. So I need to also multiply E from left with Z. But this I know to be equal to Z because E is identity. Okay. But now look at this one. I know this to be equal to identity. So E times Y, this should be equal to Y. Again, I reach that Y and Z must be equal. If you assume there are two distinct inverses of the element X, Y and Z, this leads to the observation that Y and Z must be equal. So this is a contradiction. This means you cannot have multiple inverses of any element. The inverses of each element in a group is unique. Now, the structure A with the binary operation star is called a semigroup if the operation is associative, but identity and inverse elements don't exist. So if you just drop to one axiom, we call this structure a semigroup. Okay, for instance, set of positive integers along with addition is a semigroup because you do not have an identity nor you have inverses. This is a semigroup and they have other properties that groups do not have because it's in general a more general structure. On the other hand, the structure set A along with operation star without inverses, okay, is called a monoid. Now, what we have here is identity. We have associative property, okay, associative operation, as well as identity element, okay? So to a semigroup, if you add an identity element, what you get is monoid. A monoid is not a group because you do not have inverses, but it does have an identity element. For instance, the set of natural numbers with addition is a monoid. It does have the identity element of 0, but it does not have inverses. Here are some examples, and this one is quite important in theory of computation. Let sigma be a finite alphabet, meaning a set of symbols. Sigma star is Kleene closure, the set of all strings that you can obtain by concatenation, and plus represent the concatenation operation, and this structure is a monoid because concatenation operation is associative, and you also have the identity element, the empty string, but you do not have inverses because you cannot, by concatenation, you cannot obtain the empty string from a non-empty string. You do not have inverses. So this structure is a monoid, and this elementary structure is extremely important in theory of computation, regular languages, the automata theory, and of course in programming languages theory. And the group, now we are going to more rather than general cases, we are going to special cases. And we do have, let's say, associative property, we do have identity element, we also have inverses. In addition to those, if we have commutativity, if the structure, the set A along with the operation, if it has commutative property, we call it an abelian group, okay? If this operation is commutative, we call it an abelian group, or sometimes we call this a commutative group. Now, this, of course, is the name of the famous mathematician, the Norwegian mathematician, Abel, and there is, of course, an Abel Prize, which is seen as the Nobel Prize equivalent in mathematics. So quite a significant person, I should say. So an abelian group is a group where the operation is commutative. But usually you can also see this as a commutative group. The set of integers along with addition is an abelian group, whereas the symmetry group of triangle, as we have just discussed, is non-commutative and non-abelian group. And this one, we can also describe non-abelian or abelian semigroup or monoids. This here is a non-abelian monoid. Finally, if there is an associative partial order that is defined on set A, we also say this is a partially ordered group which satisfies this property here.